Hello, welcome to this lesson of the Laplace transform tutor. Here we're going to solve another differential equation, again ratcheting up the complexity a little bit as we go. The same process applies. We'll apply the Laplace transform to both sides, collect the terms, trying to put the Laplace transform on one side by itself, and then we'll end up trying to invert. But what you're going to find is that, the previous two problems we did were pretty simple. And so when we got down to that step, inverting it back from doing the inverse transform back to get to time was pretty simple. From here on out, these problems and the ones that follow, it's going to be a little bit more difficult to invert it. It's still possible given that what we already know, but there's a little trick that we have to do. And you may have, I know that you've used it in the past, it's called partial fractions expansion. I don't want to get into it too much here because I'll review it as we go through the problem. But the bottom line is, in order to really solve anything with Laplace transforms, you pretty much have to be pretty comfortable with partial fractions expansion. I'm going to review it here, but it might be a good idea for you to go back to calculus. I know that my calculus videos cover partial fractions. Everybody taking calculus at some point has to learn partial fractions. So it's probably a good idea for you to be good at that because we're going to use it in a lot of problems. So let's just not get too far ahead of ourselves. Let's look at the differential equation. First derivative of the function x of t minus x of t is equal to 2 times the sine of t. So this is a much more realistic looking differential equation that you might see in a real differential equations course, and you have to solve that and so on. The initial condition is x at 0 is equal to 0. And notice that there's only a first derivative anywhere in this equation. That means there's only one initial condition required to solve it. So that's what's given to us. Let's go ahead and march through and do exactly what we always do. Let's take the Laplace transform of everything here. So it'll be the Laplace transform of that derivative, Laplace transform of x, and on the right-hand side, it's going to be the Laplace transform of 2 times the sine of t. So we go through the equation, applying everything everywhere, and then we will now work with this. So if you remember, we go back over here to refresh your memory, Laplace transform of the first derivative is s times the Laplace minus the initial condition, and that's what we're going to put here. So it'll be s times the Laplace transform of x minus x of 0. That's what we're going to have. Then we have a minus sign here, so everything here just comes from this. Now we have a minus sign. This Laplace of x we're just going to leave alone. We can't do anything with it yet. On the right-hand side, we have the Laplace transform of 2 times the sine of t. So for now, let's just leave it alone. We'll actually just pull the 2 out because it's a constant, and we'll just say sine of t, like that. All right? So on the left-hand side, what we have s times Laplace transform of x, and then here we have the initial condition, which we can see is 0. So really, I'll just for completeness put it there, but really it just drops away. And now let's go deal with this. What's the Laplace transform of sine of t? Well, if we look over here, the Laplace transform of sine of beta times t is beta over s squared plus beta squared. In this case, beta is 1. So it's going to be 1 over s squared plus 1. So what we'll get here is we'll have 1 over s squared plus 1. That's going to be that Laplace transform that we care about. And so what we're going to do now is we will notice that this 0 is basically just drops away. So what we're going to have then is we'll factor out a Laplace transform on the left. So we'll have a Laplace transform of x, open a parentheses, we'll have s, and then we'll have minus 1. This basically is simplifying this. The 0 drops away, we factor out a Laplace s minus 1. On the right-hand side, we'll have a 2 on the top, s squared plus 1 on the bottom. Okay, so what we have here is the Laplace transform times this term equals this term over here. We want to solve for the Laplace transform, so we're going to divide by this term right here. So we have the Laplace transform of x is equal to 2 over, we'll divide by this, will give us s minus 1 over here, and then we'll have s squared plus 1 right here. Okay, so we've basically gotten down to the point where we've done in all of these problems. We've taken the Laplace transform of both sides, we've applied our initial condition, and we've solved for the Laplace transform, which is a pure function of s. Now all we need to do is invert it, come backwards, so that we can go back to the time domain, and basically convert this to a function of x of t. But the problem is, when you look at this, 2 over this term in s times this term in s, If you look over at our table, we have absolutely nothing that looks like that. I should look at this table over here. We don't have anything that looks like that. Now, let me tell you though, we do have, this term matches part of it. The s minus lambda kind of matches this part, and the s squared plus 1 kind of matches this part. You can see how you can kind of use this guy to get that part of it over there. But unfortunately, when you see these Laplace transforms like this and this one like this, those are if they're standalone. Now we have something multiplied by something else, and you're taking the Laplace transform of the entire thing. So you cannot just apply them individually, they're multiplied together. If they were added together, sure, we can apply that Laplace transform term by term, but now we're trying to invert the whole thing. Another way to look at it is if I multiply all these s's out, I'm going to get some polynomial in s cubed, because that's the leading terms here. And I have nothing on the board over there that can invert an s cubed polynomial. When it's s cubed plus 2s squared plus 3s plus 5, or whatever it ends up being, I don't have anything that looks like that. So you're stuck for a minute. Now here's where I said that there will be some tricks, so to speak, to help you invert these things, and you need to be comfortable with them. And what I mentioned to you before is partial fractions expansion. This is a textbook partial fractions expansion there. So what we need to do is expand this in partial fractions, where one of the fractions will have the s minus 1 in the denominator, the other fraction, the other of the partial fractions, will have this in the denominator, and they'll be linked by a plus sign. That's what partial fractions does. So I can then apply these guys on the table individually to those. So I could just tell you, hey, do partial fractions on this, and you know, just kind of throw you to the wolves. But I don't want to do that because I think that's a little bit mean, and you know, we want to make sure you understand everything. So let's do a very quick review of partial fractions. All right, I'm going to give you enough of a review to kind of get us through this problem, but if I were you, I would also review what you learned in calculus, either from my videos or from your textbook. Because it's something that we're going to use a lot. So here we go. This is my informal definition of partial fractions. It's going to be written kind of in my own words. If in the denominator, meaning the denominator of whatever it is you're trying to split apart, you have any of the following. Okay, it's going to look a little weird. I'll explain it. 1 over s minus a to the mth power, then you write as the following. You write it as some constant a1 over s minus a plus some constant a2 over s minus a squared plus dot 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 plus a to the mth or sub m over s minus a to the mth power. So what we're trying to say is basically partial fractions expansion is a way to, when you have basically 2 or more terms in the denominator where they're basically polynomials in s, is basically what it's going to boil down to. Here we have s minus 1 to the first power, and we have s squared plus 1 to the first power. If you have something in the denominator where it's just s minus a number raised to a power, in this case we have s minus 1 to the first power, so it's going to be simpler. But you may have s minus a squared, s minus a to the third, s minus a to the fifth, whatever. Whatever power you have outside of the parentheses, you basically need to add that many terms. So if you have, let's say, s minus a to the first power, it's just going to be this term right here. If you have s minus something to the second power, then you'll have this term and then another constant with this guy squared. If you have 3 terms, you'll have 3 terms where you have first power, second power, third power. So whatever power you have down here, you're going to end up with that many terms. That's why it's s minus a to the mth power. All right, let me write something else underneath it. If you have, or I should say, something like this, 1 over s squared plus bs plus c to the mth power, then you write as b1s plus c1 over s squared plus bs plus c, right? Plus b2s plus c2 over s squared plus bs plus c squared. And then I'll say plus dot dot dot. Let me go ahead and scoot over a little bit so I have room. Plus dot 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 plus. And then basically bm s plus cm over s squared plus bs plus c to the nth power. All right, I know this looks kind of ugly. You know, when you explain something like partial fractions, it looks extremely complicated at first. Because when I put stuff like this on the board, I'm trying to summarize all possible cases, right? So that's why I have all these little m's running around everywhere, generalizing everything. In reality, when you have a real partial fractions problem, it's going to be much simpler, and there'll just be a few terms, and then you'll basically solve it. But basically, you're looking for two classes of the denominator, and then you can split this guy up as follows. If you have, very simply, s, notice there's no power on the s, but if you have s minus a to the nth power, then you basically have to have that many terms. Each one increases the power of the denominator. You have a single constant on the top. Here I'm calling them a1, a2, a3, whatever, a sub m, but it doesn't matter what you label the constant on the top. Ultimately, you're going to be solving for these constants there. Now, if you have a denominator that looks like a polynomial, a full-blown polynomial in S, where you have s squared plus some number times s plus c, all raised to the nth power, then you kind of have the same thing, except the top is bs plus c, and the bottom, again, you have to have that many terms, however many, what the power of m is. So here's the first power, here's the second power, third power, on up to whatever power of m you have. Each time you add a term, you have to add another bs plus c, bs plus c, bs plus c. Now, I'm numbering them here, but in reality, it doesn't matter if you call it b1, b2, c1, whatever. You just need to create some constants and solve for them. So what we want to do is we want to expand that guy there. So again, I kind of said that you need to kind of review it on your own. So what you're going to do essentially is you're going to rewrite your partial fraction expansion in terms of this on the right-hand side. Then you're going to cross multiply and solve for the constants. Now, believe me, I totally understand that this may look confusing at first or whatever, but all of you guys up to this point must have studied this in calculus. I know that I taught it in my Calculus 2 course, so go refresh your memory on that. If it's total Greek to you, you really need to understand it, or you're not going to be able to get very far with inverting any Laplace transforms, because a lot of times they do look like this. So what we're going to do now is we're going to leave this on the board, and we're going to continue with this problem. And you're going to see that it's not that big of a deal. So here we have a situation. Let me go and scoot this over, actually. I think I'd rather scoot it over so you can see both sides. The way we're going to write this is we have a Laplace transform equal to this. So we have a simple s minus 1 on the bottom, and we have a polynomial in s. Each power of these parentheses is just 1. So really what we're going to have is we're going to say that this fraction here, this whole term here, can be rewritten in terms of a partial fraction expansion. And it would look something like this: a over s minus 1 plus bs plus c over s squared plus 1. That's it in this particular case. There's only a power of 1 here, so we only need one power in s plus 1. There's only a power of 1 in here, so we only need one of these powers here. Because it's so simple, you just use a simple single constant a for this, and then bs plus c. So what we're saying is that this fraction, 2 over all of this stuff, is exactly equivalent to the sum of these two fractions here. All that remains is for us to find out what a, b, and c is, and if we can find out what a, b, and c is, then we can expand into this partial fractions representation, which, as you will see as we go on, is going to let us invert this transform, whereas right now, if we leave it like this, we can't do that. So the way you continue with partial fractions expansion is once you write out what it's equivalent to here, you need to basically multiply both sides, because there's an equal sign here. This is actually equivalent to what we have on the right. So we can multiply left and right by anything we want. We're going to multiply by the entire denominator here, the entire denominator on both sides of the equal sign. So if you do that to the left, you're just going to get a 2, because everything is going to cancel. And when you get to this term here, you're going to end up with a, and you're going to end up with s squared plus 1, because if I multiply both sides by this, then when it multiplies by this term, the s minus 1 will cancel. This will be left multiplied by a. And then you will have bs plus c, and then you will have s minus 1 over there, because when I multiply by both of these terms, it gets multiplied here, and then it also gets multiplied here. When I multiply over here, the s squareds plus 1 cancels. This is the only surviving term that gets multiplied. Notice I wrap it in parentheses to make it absolutely clear. All right? So then what you do is you do a lot of algebra. Up until this point, it's been pretty simple. But now what we're going to do is have to bust out this guy in algebra and see what a, b, and c are equal to. So what we'll do is we'll say 2 is equal to a times s squared plus a, just distributing this in. And then here we have to do FOIL because we have two binomials. So what we will have is, for the first terms, we'll have bs squared. For the inside terms, we'll have cs. For the outside terms, we'll have negative bs. And for the last terms, we'll have negative c. So we literally are just doing algebra on all of that stuff. And then we want to collect terms, but we want to collect them in groupings of s squared, and so on. So we look for the s squareds, and we see we have two of these guys. So we factor out this s squared, and it's a plus b. Don't worry about why we're doing it yet. Just realize that we're collecting these terms and factoring it out. Okay, I'll put a dot under here and under here to tell you that we've used those two terms. Now we try to collect the s terms here. And so I'll pull out an s, and I'll say c minus b, because that's factoring out an s from here. I'll put a dot under here and here to tell you we've used these terms. The only terms left is a minus c. All right? Plus a minus c. I'll just put a parentheses around that just to group it and show you. So all we've done is we've cross-multiplied, we've collected terms, we've factored everything out, and now we have, this is actually an equal sign here. So what we have basically learned is we look for s squared terms on the left. There's no s squared terms on the left, and so since there's an s squared term on the right, what we've basically figured out is a plus b must be equal to 0, because we're looking for coefficients of s squared on the left, and they don't exist, so we must set this now equal to 0. Now we look at this term, and we're looking for any terms that involve s over here, and there are none, so c minus b we now know is equal to 0. So basically both of these are 0 because this is a simpler problem. This constant, there's no s here, this constant implies that a minus c must equal to the constant term on this side, which is 2. All right? So basically what we have done is we have created a system of equations with a, b, and c. We have three variables, a, b, and c, and we have three very simple equations. So we can solve this system for a, b, and c, and you can do it any way you want, any way you're comfortable. You can do substitution, which is what I'll do here in a second. You can set it up as a matrix and take the inverse and multiply by the right-hand side. That's kind of how I like to do it. If it's a more complicated set of equations, you can use matrix methods. If you're allowed to use graphing calculators in your test, then most of these calculators have it where you can just type this stuff in and it'll calculate a, b, and c for you. You can use that if you want. But for now, since we're learning this stuff, I want to show you everything. So we're going to solve this. Guy straight out. So what I want to do first is I want to rearrange the first equation, solve for a. So a is equal to negative b. The second equation, I want to turn around and solve it for c, which is just going to be b because we move it over. And then I'm going to take these two guys and I'm going to plug it into the third equation. And I'm going to change colors for that. And so what I'm going to have is a, we said is negative b, minus c, which we now said is equal to b, is equal to 2. So what you have is negative 2b is equal to 2. And so what you have then is b is equal to negative 1. B is equal to negative 1. So that's one of the answers. And now that we have that, it's extremely easy to write the rest of it because a is equal to negative b. So we say a is equal to negative b, which we now know that it's b is negative 1. So we do the negative of that. So negative b equals negative 1 equals 1. Right? So we say a is equal to 1. And then finally, c is equal to b. And since b is negative 1, we just say it's negative 1. So now what we have is a, b, and c solved for. A is positive 1, b is negative 1, and c is also negative 1. So doing all this work gives us three constants. Now we come back up to our partial fraction expansion. Now we know what A is, now we know what B is, now we know what C is, which are all defined as numbers. So now we know that this fraction here, this whole thing, can be written in this form. That's called partial fractions expansion. So what I want to do is apply what we have here. So, all right, so now what we're going to do is use what we have expanded in partial fractions and plug in our values for A, B, and C. So on this board, we will say that the Laplace transform of x is equal to A over s minus 1, where A we have solved for is equal to 1. So it's 1 over s minus 1. And then we have plus bs plus c. B is equal to, let's see here, B is equal to -1, and C is also equal to -1. So it's negative s plus a -1, so negative s minus 1 over s squared plus 1. All right, so now we're getting somewhere. We feel like I do know how to invert this one. We've done that a lot, but this one still looks a little bit weird. But then we realize that I can bust this apart into two fractions. It's nothing to do with partial fractions, it's just regular old algebra, and you'll see what I mean in a minute. Here we can put the negative from here and call this s over s squared plus 1. This negative comes from here, 1 over s squared plus 1, right? So this comes about because we have two terms in the top linked by a minus sign, and so we can write the first term over the denominator and then the second term over the denominator. This is basically just fraction addition. If I had given you this and said, hey, add these guys together, you would say, these are the same denominator. So keep the denominator, add the numerators, this is what you get. We're just going in reverse. So now that we've done this, we now can finally actually make some progress. So because now we can say that x of t is the inverse Laplace of 1 over s minus 1 minus, from here, the inverse Laplace of s over s squared plus 1 minus, from here, the inverse Laplace of 1 over s squared plus 1. Just like that. And so then we just go term by term. We say x of t is equal to 1 over s minus 1 comes straight from here. S minus 1, where lambda is 1, we get e to the 1t. So we get e to the 1t, like this. The minus sign comes from here, and then we look for s over s squared plus 1. We see s over s squared plus 1, now beta must equal 1. So if beta is 1, then this inverts to cosine of 1 times t, which is just cosine t. All right? And then finally we have a minus sign here. This one is 1 over s squared plus 1. 1 over s squared plus 1, beta must be 1, so we have 1 over 1 sine of 1t. So what we get is 1 over 1 is 1, and we have sine of 1 times t. This is the final answer. This is what we've been trying to find. When you solve a differential equation, what you're trying to do is figure out what x of t is. What is that function that makes this true? If you take this function, x of t, and you stick it back into this differential equation, if you take its derivative and then you subtract the function itself, you're going to get this. All right, and that's basically how it works there. And the initial condition is going to hold at x of 0, you should get 0. In fact, you can kind of look at that right here. X of 0 is equal to 0. If you put 0 here, e to the 0 is 1. Here, cosine of 0 is also 1. Sine of 0 is 0. So you have 1 minus 1 gives you 0. The initial condition satisfies our solution. So real quick from the top, what we basically have to do with all of these problems is Laplace transform both sides, which we've done here with the derivative here. This carries down. Laplace transform here, we'll do in the next step. Then we plug in the initial condition from here, right? Take the Laplace transform of the right side. We factor out the Laplace transform, giving us this. Then we move it over here. This is what we need to invert. If you can invert it, great. Now, frequently you're going to have terms like this on the bottom. You need to figure out if you can use partial fractions. So what you're looking for is terms where it's just x minus a number raised to a power. You're also looking at polynomial terms, s squared plus something times s plus c raised to a power. In this case, we only have one of these terms, so it's just one constant over this guy. That's why we did this. and then here we only have one power, so it's just bs plus c over the first power of this guy. But if you had multiplicity, if you had more than one of those in terms of an exponent here, you would have to add more terms going up in the power of the denominator each time. And that gets into the messiness of partial fractions. If you have a much more complicated problem, like let's say, for instance, this problem that we were working came out to s minus 1 to the third power here, and then s squared plus 1 to the fourth power. That would make this a much harder problem because we'd have to spend a lot more time expanding partial fractions. But anyway, once we get it written down into what we think it needs to be, multiply both sides by the denominator here. So that gets rid of everything on the left, and it gets us this on the right. We distribute everything in and we collect terms, but when we collect them, we're trying to factor out an s squared, we're trying to factor out an s, and then we're trying to write a constant term. Then we make equalities. We say these two things must be equal. So if there's an s squared term on the left, in this case there's not, but if there was, we just set the coefficient equal to this. In this case, it's 0. We set the coefficient of s from this side. In this case, it's equal to 0. And then we have a constant term, which must then be equal to 2. Then we solve the system of equations any which way you want to find a, b, and c, which we found. Once we do that, we can write the partial fractions expansion, which we can do one more step to split it up further, and then the whole goal of it is to take Laplace transforms, functions of s that are all wrapped up together, multiplied, and bust them up into a lot of terms that can be individually analyzed. So what we end up with is having to inverse this one, and inverse this one, which we can then do. So as I said before, the basic technique remains the same. We want to Laplace both sides, collect everything, inverse Laplace the answer. It's just that doing that inverse sometimes can take some work. A lot of opportunity for mistakes. The partial fractions expansion can go wrong with the algebra. Solving that little system of equations to get the partial fractions can lead to algebraic errors and things like that. So you got to be careful. But ultimately, the concept of what we're doing is not hard. So make sure you can do this yourself. I encourage you to get a piece of paper and do it yourself by hand. And then follow me on to the next section. We'll just basically continue getting our bearings with solving these problems, learning how to deal with Laplace transform in practical ways, and plowing through the algebra and the solution methods step by step so that you can gain practice and confidence with the Laplace transform.